You will now be placed into the conference.
And Heidi Chen, who work as research engineers for Sebastian as well. So the outline of our webinar is going to be as follows. First, we motivate the need for a research platform. Then we basically introduce the platform that we developed, and later on open the floor for further discussions and questions that you might have. And I should note, basically, the presentation that I'm giving is a heavily condensed presentation that we earlier held in April at CPS Week in Philadelphia. And the original presentation covered about 4 hours. So we reduced the content a little bit in order to basically fit a 1-hour webinar slot. So let's motivate the need for experimentation platform. Typically, the ideal research cycle starts with the formulation of a problem that leads to an idea for involved research, which basically then gets formalized in a model. From the model, we can basically extract properties about the process that we're going to describe in order to refine the idea. And in order to basically make the formal model of acceptable practice, we actually need to reduce this to the essence and basically build the running system itself. From the running system, we can basically obtain data and basically refine our idea and update our model in a cyclic form until basically the problem is considered to be solved. So why do we actually need experimentation in that process? So first of all, humans seem to have a limitation to grasp complexity and the scale of systems. Furthermore, models are inherently, consequently, always wrong because they represent abstractions of the real world. And this problem has been around for a long time. So there's a popular quote from a book of Limits of Theory in Electrical Machine Design that was published in Liverpool in 1938, where basically we have a number of variables in an electrical machine that can be expressed, but we actually need to reduce it down to the important factors in order to derive a model. And basically that inherent problem that they had with electrical machine design also scales with up to modern systems, for example, UAVs. So, if we don't just leave with theory, how can we basically update our insight about like a process? Basically, one solution would be to just consider limitation. But basically, if we do simulation, do we actually know the appropriate scientific questions that we want to address? And actually, can we accurately express the phenomena of interest without a practical reference platform? And do we actually have enough experimental data in order to initialize and validate our simulation? So in particular for embedded systems, the questions we need to address is, do we actually accurately understand the real-world interface? Those are, for example, sensors we have in our system, actuators that need to be interfaced, and also communication interfaces between internal control buses. Furthermore, that we need to consider is timing anomalies inside the system, scattering jitter, system state, and even sometimes mundane things as processor errators that are not present in processor simulators. So why should we experiment? We need to test theoretical predictions against reality. This is best done by a reference platform that actually flies. We need to probe the influence of assumptions that we make about our model. And we also need to eliminate alternate explanations of the physical process that we run on Earth. And furthermore, based on real-world observations, we can actually unearth new phenomena and hidden factors that might lead to our refinement of the model that we're trying to develop. So in order to see what the state of experimentation is, we basically reviewed about 200 papers of respective conferences where performance evaluation is an issue. And we noticed that most of those papers, actually 80%, contain a performance evaluation. But if you basically look at how the evaluation was conducted, only 25% of those papers actually report dispersion measures. Only 60% contain a comparison to an alternative approach. Only 1% of those basically used formal comparison methods in order to basically evaluate if they're really different. 13% have a sanity check, and the average factors that were basically analyzed in the experimentation was 2. And only 0.4% of those people actually published the data that they obtained from the platform itself. Even though we tried to inquire about many of those papers, most of the data was not available even upon inquiry. So if you basically reduce it down to papers that are published in respected embedded conferences, those figures actually become even more interesting. Only 32% of those papers contain a performance evaluation, 70% do report dispersion, 80% actually contain a comparison to an alternative, but none of those papers basically do a formal comparison of their data against a competing approach. 26% have a sanity check, and 46% only report their software setup, and 0% actually publish the data that they obtained from the experiment. And we're not the only ones complaining. There have been numerous publications in the past where they basically complain about the lack of experimental rigor in systems itself. So challenges to experimentation that typically lead people to just consider theoretical formulations or basically simulations are experimentation is deemed to be expensive, time-consuming, it requires specialized expertise, and it also requires maintained equipment. And we aim to address these problems by basically making the field tester platform accessible online to other researchers. We basically provide remote access to the system that is already set up. And we basically have a public reference implementation that we can make available to the public. And we basically restricted ourselves for the public autopilot to use open source software, so that even though we make it available, there are no issues with licensing requirement. And since we basically have the equipment on our side, we also have experts to actually maintain the equipment on site. The ideal scenario of a research platform would be that you have a remote programming interface, you have the real Hexacopter flying, and you would basically also have real experiment data, and we had to reduce it down to a real Hexacopter that basically interfaces in part with hardware-in-the-loop simulation. And now I'm going to hand it over to Pi, who's going to introduce the Hexacopter platform.
All right, so I'm going to introduce the Hexacopter platform that we built. So our motivation and our goals in building this platform was to provide an autopilot case study. We wanted to use our fully field-tested and fully operational autopilot for this case study. We are going to link it to a hardware-in-the-loop or hill simulation, and then we wanted to make it user-friendly and online accessible. So the vehicle we chose was a Hexacopter, so it's basically a helicopter with 6 fixed-pitch rotors. It has an onboard heading yaw and altitude hold, and this vehicle, it was originally bought off the shelf as an RC vehicle. So it has onboard mapping for roll and pitch commands to motor speed. And even though it's a Hexacopter with 6 rotors, it actually behaves identical to a Quadrotor. However, having the 6 rotors does give it larger payload capabilities. So the first thing we had to do was develop an autopilot for this vehicle, and thus making it fully autonomous. So the screen you see here is a first revision of our autopilot. We had, the basics, IMU, GPS, serial radio for communication with our ground station. Our autopilot was running on an OMAP 3530 running QNX as an operating system. In the bottom left here, you see our first hardware revisions. It was quite messy, so later on we actually cleaned this up and we actually upgraded some of our sensors as well. So most notably, we upgraded our GPS to 20 Hz and our IMU to a 100 Hz version. As well, we updated our processor to an AM3359 Cortex A8. And as you can see in the bottom left, we cleaned up the hardware a lot and put it into a crash cage to protect it. So after we developed our autopilot, we conducted a series of field tests to verify, that our autopilot is fully functional for real missions. So we did a series of 4 different tests. So I'm going to go through them one by one. So the first test we did was a simple GPU verification. So the idea here was that we had an experiment which consisted of real-time safety monitoring using a GPU. So we hooked this monitor onto our autopilot, and during flight, we were streaming it real data from the autopilot for the safety monitor to verify. Our second mission was a 3D mapping mission. So here we flew over a lake and took a series of still images, which we could then later stitch together. So the image you see on your screen right now, on the left half, you see the stitched image of the lake that we took, and on the right side is the satellite equivalent that we got from Google Earth. So you can see that using our approach, we were able to get very nice high-resolution images of large areas. And here is the digital elevation model that we created using the same set of still images of the lake. We also carried out thermal inspection. So here we had a thermal camera as our payload, and we flew over a large solar farm in Ontario. And while flying over the solar panels, we were able to get the thermal profiles of the different panels, as well as construct a digital elevation model, which you see in the bottom right as well. The motivation for this was to identify thermal anomalies and potential faults in the panels very quickly as we flew over them. The last mission we did was we actually went to Newfoundland over the summer, and we flew over an iceberg. So the motivation for this is that it's very dangerous to get close to icebergs because they tend to break off and roll over, and they pose a safety hazard to things such as oil rigs. So we actually wanted to deploy GPS tracking beacons using our UAV onto the icebergs. So here you can see in the bottom left, we actually took off from a fishing boat, carried a GPS beacon payload over the iceberg, and deployed it. So there are various challenges to live experiments. So obviously, when you're flying a real UAV, especially when you're carrying out an experiment, there's a high risk of crashes because you're changing parameters all the time. This poses a large risk for damaging the UAV, as well as a potential hazard to the environment and various personnel. As well, experiments using real live UAVs have a lot of overhead. UAV flights are always weather dependent, and in Canada they require special flight operation certificates, which may get declined if the test is hazardous, and it also has long lead time. So in general, we found it took about a month for us to get it approved, and you needed a special certificate for each unique location you're flying in. As well, it's very difficult to scale such experiments because the flights are always blocked on the number of UAV operators available. So it's very difficult, especially for researchers from remote areas, to access the platform. So to solve some of these issues, traditionally researchers, we turn to simulation. So using simulation, in traditional software simulation, both the autopilot and the vehicle dynamics and environment are simulated. However, this is mostly used to test software algorithms, and there's a lot of shortcomings. One step up is the hardware-in-the-loop or HIL simulation. Here, the vehicle dynamics and environment are still software simulated. However, the autopilot is using the real hardware and software. So we actually take the physical autopilot and connect it to a software simulation. What this allows us to do is test the whole autopilot entity as a whole, and then test all the communication interfaces as well, as if it was actually flying. So in a traditional HIL simulation, this would be the loop. So you would take your real autopilot, you would send the actuation commands into a HIL simulation box, which would then, using software, propagate the various vehicle states, and then it would generate sensor messages mimicking real sensors, sending it back to your autopilot. So now I'm going to quickly go over the dynamic model of our vehicle. So it is a hexacopter. However, it behaves analogous to a quadrotor. So I'm actually going to give the model for a quadrotor. So the basic operating principle is that you have fixed pitch rotors. And using the thrust differentials between opposing rotors, we create a moment to control pitch and yaw. The rotors are also counter-rotating. So as you see in the bottom right, and based on the speed differentials of adjacent rotors, or the counter-rotating pairs, we could create a yaw moment. So before we go on with the model derivation, we'll first define our frames. So first, we have a global frame, which we will define as northeast down. Then we'll have a body fixed frame. And then we will have standard Euler angles to define roll, pitch, yaw as phi, theta, and psi. The individual rotor thrusts as F1 to 4, and the angular velocities as capital omega 1 before. So we start with the standard Newton-Euler equations of motion. So we have the equation for translational motion as well as rotational motion. So here we have the mass of the vehicle as m, x denoting the position states in a global frame, j as our inertia matrix, and lowercase omega as the standard body rates. So the sum of the external forces can be broken down into the component due to gravity, a component due to aerodynamic drag, which will approximate as a constant times a constant proportional to the square root of the velocity of the vehicle, as well as the component generated from the thrust of the rotors. So here the total thrust will be F, and then we'll rotate this into the global frame from our body frame using this rotation matrix you see at the bottom here. The sum of the external torques can be expressed as the term GA, which is the gyroscopic moments caused by the rotor and the body rotation, given by this equation, as well as the torque moments generated by the thrust differentials used to actually actuate the vehicle, which is given near the bottom of the screen here. So right now, the rotational part of the model, so previously we defined our roll pitch yaw as Euler angles. However, the Euler equation using lowercase omega is in standard body rates. So we have to do a conversion from PQR to standard Euler rates using the first matrix you see on the top here. So if you put it all together, this yields the following equation for rotational motion, with the M matrix being the mass matrix, which you see on the bottom here, times the second derivative of all your Euler angles, plus this K, which gets really messy once you expand it out, as you can see on this slide. So from this model, we notice a few things. So first is that there are a lot of unknown parameters that you cannot directly measure. So if I'm given a vehicle, it is very difficult to correctly system identify all these really intricate, inertias and masses and different constants. As well, as soon as I switch any hardware on the vehicle, it's very likely that I have to resystem ID the whole vehicle. As well, models are never completely accurate. It's very hard to account for all factors. And so it generally just does an approximation. So in order to get a more accurate system, we decided to replace as much of the hill simulation with the physical system as possible. So before, in our hill simulation, we would have our autopilot on the left and a simulation on the right of the positional and attitude states. So instead, what we're going to do is that we decided to put our real field-tested vehicle on a tilt stand with the real IMU providing the attitude states of roll, pitch, and yaw. And we will only use the software to simulate the GPS states, which we cannot achieve indoors. So as far as the software stack, our autopilot software is running on RT Linux on a TI AM3359. It contains a mission planner, control laws, and a basic communications interface. It communicates to our Hill software through UART. And then on the Hill software, we have the basic simulation logic, a position simulator, which basically mimics the GPS, and an AHRS interface, which connects to the IMU to get the IMU readings. So the basic control flow is that we obtain the vehicle position. It goes into the mission planner, which has a global reference position which the vehicle is trying to get to. This gets input into a position controller, which generates a yaw compensated acceleration. This and the vehicle yaw converts the desired acceleration to an attitude, which is used as a reference attitude into our inner loop controller. And then this, as well as the current roll and pitch of the vehicle, gets put into our inner loop controller, which converts it to a PWM, which gets output to the motors. Our mission planner, the goal of the mission planner is to basically keep the vehicle on the desired flight path. There are various strategies such as trajectory tracking and path tracking. We decided to go with a very simple path tracking carrot on a stick approach. So how this works is that we have a UAV and a desired position. Using this positional error, we have the UAV move towards the desired position. Then in the next time step, keeping the same carrot distance, we advance the reference position forward by the carrot distance, and then that becomes the next position that the UAV tries to get to. Our positional controller is done using two decoupled control loops, one for the X position and one for the Y position. Its goal is to calculate a desired acceleration in the global frame. We implemented it using a lead lag controller, which we developed using root locus, and here you can see the controller, the form of the controller given here. So here on the bottom right, you have the basic position response that is typical in simulation. So after we have the desired acceleration in the global frame, we have to rotate it into the body frame using the rotation matrix here. And then using this body fixed acceleration and this triangular relationship, we can figure out the desired roll and pitch. So as I mentioned previously, our helicopter, because it was originally an RC unit, it has an onboard flight control to map the desired roll and pitch to a very rough PWM command. However, it performed very poorly when we just used the onboard flight control, as you can see in the top right graph. So in order to improve the performance, we closed the loop again using a simple proportional controller. And then this stabilized our roll and pitch greatly and gave us a lot finer control. So I'm going to hand it over to Thomas, who will link you to a YouTube to give a quick demo of our system.
So what I'm going to present now is basically the result of the live demo that we did at CBS week, where we basically set up the Hexacopter, we connected the live video link, and then basically opened it up to the audience in order to basically experiment with the helicopter. Unfortunately, this conference system, doesn't really support live video, so we basically pre-recorded the video and we're making available on YouTube. How do I paste in the YouTube? Okay.
It should be right behind you.
So I'm just going to paste in the YouTube link so they can actually. Okay.
Yep. And then go right here.
Yep. So where do I paste it in?
Krista, how do we send a YouTube link to everybody?
You can use the chat box.
Okay.
So just use the drop down at the top.
Oh, here. Just hover around here.
Okay.
And then chat.
Yeah, hover over the green.
Okay.
Okay. So that video basically displays a split screen where the top part actually outlines the web interface that you can basically see through a browser, and then basically the bottom part is the live video that was basically merged with the web interface of the Hexacopter itself. And the Hexacopter itself can be programmed through Secure Shell, or if you basically set up your development environment inside Eclipse. You can also basically connect through Eclipse through SSH to the Hexacopter directly. The system itself also has GCC installed, so you can basically recompile the autopilot on the system itself and then basically run it on the system itself as well. So it's basically a fully self-contained development environment. So let me go back to the presentation. Okay.
Do you want to quickly explain the YouTube video?
We'll explain in the process. Okay. So basically the objectives of the live demo are CBM so basically to demonstrate the remote access to the platform and then basically evaluate the runtime performance of the autopilot, whether it gets influenced by different compiler settings of GCC, or whether we actually need like real-time design constraints in order to basically run the autopilot, and what the effect of the absence of the real-time constraints were. So the setup that we had was we basically had our system under test, which was the autopilot that was basically running on the Hexacopter itself. That was interfacing through a UART to the Hexacopter hill. The user of the system could connect remotely to the system itself. So at CBS week, we had Yasir in Waterloo, and we were basically presenting an Philadelphia, and all we needed was like a secure shell connection and web browser interface in order to basically interact with the autopilot on the system itself. So this is basically the display how the browser-based interface of the autopilot looks like. We basically position the HRS system very close to a hall that we have in north of Waterloo to basically put it on a reference map. And basically at the bottom you basically see the actual position versus the desired position, so you can basically see the tracking while the hexacopter is actually moving on the stand and basically executing the autopilot. So what we used as a platform in order to run the autopilot is Realtime Linux. There are many flavors of making Linux real-time. They have a soft real-time patch that is now contained in most of the Linux systems, but what we opted for was an external patch, which is called the Preempt-RT or Preempt-RT hard patch that basically replaces many of the kernel spin locks with mutexes and also increases the frequency at which the kernel can be interrupted. And basically by that patch, you can significantly reduce the jitter on Linux systems itself. We have opted for Linux because the source code is freely available, and also we have the full toolset of Linux performing monitoring tools, so there are no issues with licensing restrictions to basically experiment with the platform itself. So what we used in Philadelphia was basically the Linux perf tool, where if you download the source code for the autopilot from the CNC website, you'll basically get a makefile that already has like several predefined perf targets, where you can, for example, experiment with performance counters of the kernel. You can also basically look at various configurations of perf to do basically do memory profiling itself. And the beauty of perf is it actually supports many architectures. So you get perf for kernels for x86, 64-bit, PowerPC, and also various ARM platforms. So basically many of the kernel pointers were also available on the AM335X, which is basically an ARM Cortex-A8 processor itself. Other tools that can be used on the platform is, for example, Valgrind. It's basically an instrumentation framework where you can basically build profilers and do memory profiling or various other detections, for example, memory leak detection. You can also use pin, DynamoRear, or dyninst on the platform itself, and you can also use cache grind, which is part of Valgrind, in order to basically do cache and branch prediction. So other tools that you can also look at the platform is VMstat. You can also do coverage analysis on the autopilot itself. Since we basically freely provide the source code of the autopilot, you can actually basically change various implementation parameters of the autopilot and actually see how coverage is, for example, implemented. Or basically you can also use the GNU profiler in order to basically profile functions itself. And if you apply the Preempt-RT patch to Linux, you can also enable an option that allows you to look at various performance histograms. So you could basically try to figure out why does, for example, a wake-up timer take more time than expected. So the first experiment that we basically opened up to the public was to basically let them experiment with various compiler settings. And this would be the overview of the optimization levels that you could basically achieve with GCC on that platform. So I'm not going to go into details. I'm just going to move over here. So we basically also got like various results, for example, variation on the memory allocation between the various optimization levels. It was not necessarily significant, but one saw some change on the dispersion of the memory allocation. The other thing is that we notice is the optimized for size that basically also increases the variation of page faults quite significantly between runs. And the next experiment that we open up to the public is, do we actually need real-time design patterns for the autopilot in order to basically run the system? And what you can do in RT Preempt is you can basically disable the real-time priority and basically just put the autopilot on the real system priority. And the other things that autopilot does, or basically our implementation is, it tries to pre-fault the entire memory in order to make sure that during operation you don't get any page faults that could basically influence the latency of the control loop. and you could basically experiment what would happen. And actually, during the demo, we saw several instances as we disabled those measures that the Hexacopter would have crashed in the field itself. So by being on this stand, we can actually limit the physical harm to the Hexacopter, even though we open up the, basically free modifications to the autopilot itself. So we basically looked at, for example, how the context switches get influenced, and you basically see those tabs over here. And we also implement various safety measures, for example, deadline overrun detection. So if the control loop basically detects that there's a deadline overrun, it basically shuts itself down. And basically in the case where the Hexacopter would have crashed, you basically see that there's like a much smaller frequency of samples, and that's why basically this last column is like so reduced towards the other ones. The other thing we did is we basically disabled like safety and basically let the control loop run anyway. And we also saw like quite a number of elevated measures on the other parameters that we collected. So page faults, similar thing. And then non-real time, basically runtime measures. And basically those figures really depend on how you instrument your autopilot. And I believe James has a set of slides to basically explain how to access the platform remotely. Over. So I would just open up the floor for discussions, or I think James also has like some presentations how to access the platform through CMC's network.
Yeah, I can present my slides. There's only 3 slides, and then we'll open it up for discussion, I think.
Go to desktop through James.
Yeah. I think Krista's doing that.
Krista will take care of that. Okay, so for those who would like to access the Hexacopter online, these slides are for you. And it's fairly simple. You just need to make sure you have an account with CMC Microsystems. Probably most of you on the line already do. And if you don't, then that red circle in there shows you where on our webpage at www.cmc.ca, where you can get an account. And your supervisor should have a subscription to CMC Microsystems as well. And then once you have that, let the lab manager, Summit Segal, know that you intend to use it and when, and let myself know as well so that I can add you to an access control list. So also in that red circle there's a sign-in button. So after you've got an account, you sign in, let us know, and you proceed to where you normally see the list of design tools that you can get from CMC. And in there's a link to something called CAD Pass. If you use our tools, you've probably already installed it. It brings up the AppGate client software. And in there, where you can select all the design tools, once your name is added to the access control list, you'll see a folder there, Waterloo Real-Time Embedded Systems Lab. And then just to the bottom right of the slide, after clicking on that folder, you'll see what you can get from the lab through this online system. And right now, it's just the Hexacopter, which is that little gear icon there, enable access to autopilot systems. So you click on that, and it would give you a green check mark. And then a little window will come up, and it will say to access the autopilot, the URL is Waterloo Resol Autopilot 01:3000, and that would bring up your development environment. So on the Hexacopter itself, the complete development environment for you to edit and compile what's there. The simulator that you saw earlier, where there's the picture of the Hexacopter on a map of the Waterloo campus, and then a few graphs there showing you the roll, pitch, and yaw, will come up in the simulator in the other URL. And the hill controller, that runs on QNX, and we just need to talk to the lab manager about how we can get get you connected with QNX so you can have the tools you need to compile and run anything there. But most people will just modify the autopilot and look at the outputs from the simulation. This is all detailed in a user guide, which will be available shortly from CMC's website. Just send me an email to get it right now. And there's also, I should let you know, there's also in the user guide, it talks about a Skype connection so that you can view the hexacopter. So as you run your autopilot code, you can see how it tilts on a stand in the lab and collect some data. If you need to connect up any other instruments to the hexacopter that are in the lab, then the lab manager can probably make arrangements to do that for you as well. So this lab and this product, they're a part of the MCAN project, a national project managed by CMC Microsystems, and it's there for your academic research purposes. If you have any trouble and need more help, just give me an email at jr@cmc.ca. And that's it. I think we should open it up to questions now.
Thanks, Dan.
Close, check your lounge.
Hello?
Hi.
Hello?
Yeah, I think if somebody just speaks up, then we'll take it that way. No? Okay. Well, if there's no questions, then thank you very much. And tomorrow there's a webinar on the data mill, also offered through the lab. Hope to see you there.
Awesome. Thank you so much.
Thank you, Yasser. Thank you, Thomas. And thank you, Pi. Great job.
Thank you.
Thank you.
Bye.
Thanks.